Yes, welcome all to the online classes. Today, I'm going to take physics BTech fourth semester. And the topic is the wave nature of light. So, the wave nature of light. Light is an external physical cause uh, which excites our sense of sight. Light can travel in a vacuum. Light can travel in medium like air, water, glass. The medium is said to be transparent if it transmits all the light which falls on it without any appreciable loss. Example: water, air, glass, mica, etc. A medium is said to be opaque if it does not allow any light to pass through it. Example: the sheet of paper, metal foil, piece of wood, etc. There are some mediums which transmit a part of light, but it is not sufficient to identify a body, that is, to see the body through such a medium. It is called translucent. Example: ground glass, oil paper, etc. A ray of light is the direction in which light moves. A bundle of rays is called beam. A very narrow beam of light is called a pencil. A convergent beam means the rays in the beam move towards one point. A divergent beam means rays in the beam spread out from a point. When the rays constituting a beam are parallel, the beam is said to be parallel. It may be noted that the light itself cannot be seen, but it is the light which makes objects visible. A self-luminous body is the one which is capable of producing light by itself. Example: sun, star, candle, flame, etc. A non-luminous body cannot produce light by itself. Example: moon. Each point of luminous body is source of light. So, uh, this is a, a general definition of light. Now, the nature of the light and the contents related to it is wave versus particle nature, that is Huygens principles and diffraction, Huygens principles and the law of refraction, interference, Young's double slit experiment, the visible spectrum and dispersion, diffraction by a single slit or disk, diffraction grating, the spectrometer and spectroscopy, interference in thin films, Michelson interferometer, polarization, liquid crystal displays, scattering of light by the atmosphere. Now, start with introduction of light. Light is the basic to almost all life on Earth. Light is a form of electromagnetic radiation. Light represents energy transformed from the source to observer. Many phenomena depend upon the properties of light. Seeing a TV or a computer monitor, blue sky, colors at sunset and sunrise, images in mirrors, eyeglasses and contacts, rainbows, and many others. These are the some day-to-day phenomena which depends on the properties of light. Lights and optic. There are two historical models for the nature of light. The speed of light has been measured in many ways. Reflection and refraction are the fundamental phenomena in ray optics or geometric optics. Internal reflection is the basis for fiber optics. So, in fiber optics technology, internal reflection is the basic principle of moving a light in fiber optics. The nature of light. Before the beginning of the 19th century, light was considered to be a stream of particles. The particles were either emitted by the object being viewed or emanated from the eyes of the viewer. Newton was the chief architect of the particle theory of light. He believed the particles left the object and stimulated the sense of sight upon entering the eyes. The alternative view, Christian Huygens argued that light might be some sort of wave motion. Thomas Young in 1801 provided the first clear demonstration of the wave nature of light. He showed that the light rays interfere with each other. Such behavior could not be explained by particles. Christian Huygens from 1629 to 1695, the brief about best known for contribution to the fields of optics and dynamics. He thought light was a type of vibratory motion. It spread out and produced the sensation of light when it hit the eye. He deduced the laws of reflection and refraction. He explained the double refraction. Now, the confirmation of wave nature. During the 19th century, other developments lead to general acceptance of the wave theory of light. Wave theory of light. Thomas Young provided evidence that light rays interfere with one another according to the principle of superposition. This behavior could not be explained by the particle theory. Maxwell asserted that light was a form of high-frequency electromagnetic wave. Hertz confirmed Maxwell's prediction, and particle nature. Some experiments could not be explained by the wave model of the light. Newton thought that light is made up of tiny light and elastic particles called corpuscles, which are emitted by luminous body. The corpuscles travel with a speed equal to the speed of light in all directions in straight lines. The corpuscles carry energy with them. When they strike retina of the eye, they produce sensation of vision. The corpuscles of different color are of different sizes. Red corpuscles larger than the blue corpuscles. The corpuscular theory explains the following fact. Light carry energy and momentum. First of all, that is, light is having the energy and the momentum. Light travels in a straight line. Propagation of light in vacuum, that is, light can be travel or propagate in vacuum also. And the corpuscular theory also gives the laws of reflection, laws of refraction. A major prediction of the corpuscular theory is the speed of light in denser medium is more than the speed of light in rarer medium. But this turned out to be wrong when velocity of light was measured in water. The truth is that the speed of the light is smaller in denser media. Therefore, the Newton's corpuscular theory is wrong. Furthermore, the corpuscular theory fails to explain interference, diffraction, and polarization. Interference was discovered in 1800 by Young's. Two corpuscles coming together cannot destroy each other. So, this is the Newton's corpuscular theory. The photoelectric effect was a major phenomenon not explained by the waves. When light strikes a metal surface, electrons are sometimes ejected from the surface. The kinetic energy of the ejected electron is independent of the frequency of the light. Einstein in 1905 proposed the explanation of the photoelectric effect that uses the idea of quantization. The quantization model assumes that the energy of a light wave is present in particles called photons. E is equals to h nu, where h is known as the Planck's constant and is equals to 6.63 into 10 to the power minus 3 4 joule second. Dual nature of light. In view of these developments, light must be regarded having a dual nature. Light exhibits the characteristic of wave in some situation and the characteristic of particle in other situation. So this chapter investigates the wave nature of light. Measurement of the speed of light. Before investigating the nature of light, first we come to the topic that what is the speed of light, that is how you just measure the speed of light. Since light travels at very high speed, early attempts to measure its speeds were unsuccessful. uh, Remember, c equals to 3 into 10 to the power 8 meter per second, that is the speed of light. Galileo tried by using two observers separated by about 10 kilometers. The reaction time of the observer was more than the transmit time of the light. Measurement of the speed of light. Römer's method. Yes. Römer's method. In 1675, Ole Römer used astronomical observations to estimate the speed of the light. He used the period of revolution of a moon of a Jupiter as Jupiter revolved around the sun. The angle through which Jupiter moves during 90-degree movement of the Earth was calculated. So this is some pictorial representation. In the time interval during which the Earth travels 90 degree around the Sun, 3 months, the Jupiter travels only about 7.5 degree. The period of revolution were longer when the Earth was receding from Jupiter, shorter when the Earth was approaching. Using Römer's data, Hygiene estimated the lower limit of the speed of light to be 2.3 into 10 to the power 8 meter per second. This was important because it demonstrated the light has a finite speed as well as giving an estimate of that speed. Measure of the speed of light by Fizeau's method. This was the first successful method for measuring the speed of light by means of purely terrestrial technique. It was developed in 1849 by Armand Fizeau. He used a rotating tooth wheel. The distance between the wheel, considered to be the source, and mirror was known. This is the pictorial representation of Fizeau's method to calculate the speed of light. D is the distance between the wheel and the mirror. Delta t is the time for one round trip. Then speed is equals to distance upon time taken. That is 2d, the round trip time distance 2d, and the difference or time taken to complete the trip. Fizeau found a value of c equals to 3.1 into 10 to the power 8 meter per second. Now, the Ray approximation in ray optics. The Ray approximation in ray optics ray optics, sometimes called geometric optics, involves the study of the propagation of light. It uses the assumption that light travels in straight line path in a uniform medium and changes its direction when it meets the surface of a different medium and changes its direction when it meets the surface of different medium or if the optical properties of the medium are non-uniform. The ray approximation the ray approximation is used to represent the beams of light. Ray approximation, the rays are straight lines are perpendicular to the wavefronts. The rays which are always point in the direction of the wave. Propagations are straight lines perpendicular to the wavefronts. With the ray approximation, we assume that a wave moving through a medium travels in a straight line in the direction of its rays. Now, according to the Huygens wave theory, the wave theory of light was given by Christian Huygens, as we had seen, we had gone through 1629 in 1695. According to this, a luminous body is a source of disturbance in a hypothetical medium, either this medium pervades all space, it assumed to be transparent and having zero inertia, the disturbance from the source is propagated in the form of waves through the space. The wave carries energy and momentum. I can assume that the waves were very longitudinal. Now we know that there does not exist any medium like ether. The experiment of Michelson Morley failed to detect any medium like ether. Further, when polarization was discovered, then to explain it, light waves were assumed to be transverse in nature by Fresnel. Other essential features of the wave theory of Huygens are correct. This theory explains successfully the phenomena of interference and diffraction apart from other properties of light known at that time. The wave theory introduced the concept of wavefront. So the wave theory introduced the concept of wavefront. Huygens gave a geometrical construction for explaining propagation of wavefront. So now wavefront is a surface connecting all those points which have same phase of vibration. Wavefront is the locus of same phase points. The shape of the wavefront may be spherical, cylindrical, plane, or any other shape. Depending on the shape and size of the source, a point source gives a spherical wavefront, a line source gives a cylindrical wavefront, a source at infinity gives a plane wavefront. A line drawn perpendicular to wavefront is called ray of light, and represents the direction of propagation of the light wave. So, this is the wavefront explanation. With the ray approximation, we assume that the wave moving through a medium travels in a straight line in the direction of its rays. If a wave meets a barrier with lambda very less than d, the wave emerging from the opening continues to move in a straight line. D is the diameter of the opening. As you see in the figure, when lambda is very less than the d, the rays continue in straight line path and the ray approximation remains valid. There may be some small H effects. This approximation is good for the study of mirrors, lenses, prisms, etc. Other effects or the other effects occur for openings of other sizes. Reflection of light. A ray of light, the incident ray, travels in a medium. When it encounters a boundary with a second medium, part of the incident ray is reflected back into the first medium. This means it is directed backward into the first medium. For light waves traveling in three-dimensional space, the reflected light can be in directions different from the direction of the incident rays. Specular reflection. Specular reflection is a reflection from a smooth surface. The reflected rays are parallel to each other. All reflection in this text is assumed to be specular. Diffuse reflection. Diffuse reflection is a reflection from a rough surface. The reflected rays travel in a variety of directions. A surface behaves as smooth surface as long as the surface variations are much smaller than the wavelength of the light. Now, laws of reflection. The laws of reflection, as you see in the figure, a ray is incident on some surface and it gets reflected back with some sort of angle. The incident ray, the reflected ray, and the normal all lie in the same plane. So, the incident and the reflected and normal to these two lie in the same plane. So, the normal is a line perpendicular to the surface. It is the point where the incident ray strikes the surface. The incident ray makes an angle of theta 1 with the normal. The reflected rays make an angle of theta 1 dash with the normal. The law of reflection is incident I is equals to R. The law of reflection is basically the I equals to R, where I is the angle of incidence, the angle which the incident ray makes, with the normal, and R is the angle of reflection, that is theta 1 dash, the angle which the reflected rays make with the normal. Huygens principle of wavefront construction lead to this law. So, the angle of reflection is equal to the angle of incidence. This is the first law of reflection. This relationship is called the law of reflection. The incident ray, the reflected ray, and the normal all lie in the same plane. Because this situation happens often, an analysis model wave under reflection is identified. Notation note: the subscript 1 refers to the parameter of the light in the first medium. If the light travels in another medium, the subscript 2 will be associated with the new medium, which will be used later on. Since the reflection of waves is common phenomena, we identify an analysis model for this situation, the wave under reflection analysis model. Multiple reflections. The incident ray strikes the first mirror. The reflected ray is directed towards the second mirror. There is a second reflection from the second mirror. Apply the law of reflection and some geometry to determine information about the rays. So this is the multiple reflection phenomena which you see through the figure. A ray is incident on the first mirror, then the reflected ray incident on the second mirror, which is just like an incident ray for the M2, and then from the M2 one ray is reflected with theta dash M2 angle. Retroreflection. Assume the angle between two mirrors is 90 degree. The reflected beam returns to the source parallel to its original path. This phenomena is called retroreflection. If two mirrors are at 90 degree, the reflected beam returns to the source parallel to its original path, then this phenomena is called retroreflection. Application includes measuring the distance of the moon, automobile tail lights, traffic signs. Refraction of light. When a ray of light traveling through a transparent medium encounter refraction. Now the second topic is the refraction of light. The bending of light as it passes from one medium to another is called refraction. Refraction of light occurs because light travels with a different speed in different medium. In vacuum, the speed of light is 3 into 10 to the power 8 meter per second. In glass, the speed of light is 2 into 10 to the power 8 meter per second. In water, it is somewhat 2.25 into 10 to the power 8 meter per second. The slowing down of the wave in medium causes it to bend towards the normal. Causes it to bend towards the normal. So, when a ray of light traveling through a transparent medium encounters a boundary leading into another transparent medium, part of the energy is reflected and the part enters the second medium. The ray that enters the second medium changes its direction of propagation at the boundary. The bending of the ray is called reflection or refraction. The bending of the ray is called refraction. The incident ray, the reflected ray, the refracted ray, and the normal all lie on the same plane. The angle of refraction depends upon the material and the angle of incidence. So sine theta 2 upon sine theta 1 equals to V2 upon V1. V1 is the speed of the light in the first medium and V2 is the speed of light in the second medium. The path of the light through the refracting surface is reversible. Just have a look in this pictorial representation or the diagrammatic representation of refraction of light. All rays and the normal lie in the same plane, and the refracted ray is bent toward the normal because velocity of a light in the second medium is less than the velocity of light in the first medium or in the air. So the light travels through the glass with some lesser speed. Now, incident ray, some of the part get reflected and some of the part get refracted, that is pass on in the glass medium, and the light gets slightly bent towards the normal. So this banding of light is known as refraction of light. For example, a ray travels from A to B. If the ray originated at B, it would be follow the line AB. It would be follow the line AB to reach point A. Following the reflected and refracted rays, this is a pictorial representation to demonstrate which one is the reflected, which one is the refracted. Ray 1 is the incident ray, ray 2 is the reflected ray, ray 3 is the refracted ray into the lucite, ray 4 is the internally reflected in the lucite, ray 5th is the refracted as it enters the air from the lucite. Light may refract into a material where its speed is lower. The angle of refraction is less than angle of incidence. The angle of refraction is less than the angle of incidence. That is, theta 2 is less than theta 1. The ray bend towards the normal. And this is the basic principle of refraction of light. The ratio, okay. When the light beam moves from air into glass, the light slows down upon entering the glass and its path is bent towards the normal. Light may refract into a material where its speed is higher. The angle of refraction is greater than angle of incidence. The angle of refraction is greater than the angle of incidence. So we come to the conclusion that when light travels from rare medium to denser medium, its velocity goes decreasing and the bending of light takes place, and the bending of light is more towards the normal. Now if the situation is reversed, if the light travels from denser to the rare medium, then the bending of light takes place away from the normal, which makes larger angle than the making larger angle from the normal, because as we know that in air or air medium the velocity of speed of light will increase on. Okay, so light may refract into the material where its speed is higher. The angle of refraction is greater than the angle of incidence. A ray bends away from the normal. Light in medium. Light enters from the left. The light may encounter an electron. In a pictorial representation, if you see that a light enter in a medium from the left hand side, it encounters to an electron. The electron may absorb the light, oscillate, and re-radiate the light. The absorption and radiation cause the average speed of the light moving through the material to decrease. This is the reason why the speed of the light get decreases in any denser medium. Now the index of refraction. The speed of light in any material is less than its speed in vacuum. The index of refraction, that is n of medium, can be defined as n equals to speed of light in vacuum upon speed of light in medium. That is n is equals to c by v. The ratio of the sine of the angle of incidence to the sine of angle of refraction is constant, whose values depend on the nature of the two mediums. If the medium 1 is vacuum, then V1 equals to C, and the index of refraction of the medium with respect to the vacuum is C by V. The fact the speed of light varies from medium to medium has an important effect on the wavelength of light. When a light ray enters in a medium, its wavelength changes. Then the relationship is wavelength in a medium is equal to wavelength in air upon index of refraction, that is n. Thus, in denser medium, the wavelength decreases. The frequency of wave does not change as it goes across the boundary. This is the very important parameter, a very important fact. The frequency of wave does not change when as it goes across the boundary, that is from one medium to the second, because there are same number of wavefront passing from medium first into the medium second. So the frequency of light, whatever the frequency of light in any medium, is equals to whatever the frequency of light in air. Thus, when a light ray from a rarer medium is reflected into a denser medium, its velocity decreases and wavelength decreases, but the frequency does not change. Index of refraction is a dimensionless number greater than unity. For vacuum, it is n equals to 1. These are the some refraction of indices of some material. Indices of refraction for cubic, diamond, fluorine, fused cord, gallium phosphide, glass ground, glass flint, ice, polysporine, sodium chloride. These are the some substances, and their refraction indexes are given in front of them. So make a note of this. Next. Now, before starting to the frequency between media, we would like to furthermore get more discussion on the success and the failure of the Huygens theory. The original Huygens theory explained refraction, and interference, diffraction, but fails to explain polarization, because Huygens assumed that the light waves are of longitudinal type. The propagation of light in a straight line can be approximately explained in ignoring the diffraction effect at the corners of the obstacle. The polarization can be explained by assuming transverse nature of light. Two drawbacks of Huygens wave theory are, so mainly there are two drawbacks of Huygens theory. One is it assumes the existence of an hypothetical medium, ether, for propagation of light. Now we know that there is no such medium. Light can travel in vacuum. And the second drawback of Huygens wave theory is silent about the nature of light. Huygens assumed that light waves are like sound waves, but now we know that this is not true. The light waves are electromagnetic waves. Further, the Huygens theory fails to explain the photoelectric effect, Crompton effect, etc. So, the electromagnetic wave nature of light was given by Maxwell in 1865, gave the theory that the light is an electromagnetic wave of some appropriate wavelength and frequency. The fact that a changing electric field produces a magnetic field, whereas changing magnetic field produces an electric field, suggests that it should be possible to propagate an electromagnetic wave through empty space or vacuum. The electromagnetic wave has the following properties. Uh, as we know that electromagnetic wave is electric field and magnetic field such that E cross B is always in the direction of propagation of wave, and electric field and magnetic field always oscillate in the phase, and the magnitude of electric field and magnetic field are related in vacuum by B equals to E by C. The velocity of electromagnetic wave in vacuum is given by C equals to 1 upon root mu naught upon epsilon naught, which is equals to 3 into 10 to the power 8 meter per second. And the velocity of electromagnetic wave in medium is given by V equals to 1 by root mu or epsilon, or it can be written as root mu naught epsilon into root mu r epsilon r. Therefore, the refractive index of the medium n is equals to C by V. We know that. So this is Maxwell formula for refractive index, and we had seen the refractive index of some substances in a slide before. So the frequency between media, which I had already discussed, or which I had already told you that it will not going to alter. The frequency will not going to alter. As the light travels from one medium to another, its frequency does not change. Both the wave speed and the wavelength do change, and almost they are decrease if they are from rare to denser medium. The wavefront do not pile up, nor are they created or destroyed at the boundary, so frequency must stay the same. As the wave moves between the medium, its wavelength changes, but its frequency remains constant. Index of refraction, the frequency stays the same as the wave travels from one medium to another. So nu equals to f lambda, or V equals to f lambda. F1 equals to F2, but V1 is not equals to V2, so lambda 1 is not equal to lambda 2. The ratio of indices of refraction of two media can be expressed as the various ratios. The index of refraction is inversely proportional to wave speed. As the wave speed decreases, the index of refraction increases. Higher the index of refraction, more it slows down the light, the wave speed. The previous relationship can be simplified to compare wavelengths and indices, and it can be written as lambda 1 n1 equals to lambda 2 n2. If in a year n1 equals to 1, the index of refraction of the material can be defined in terms of wavelengths n equals to lambda upon lambda n. So this is all for today's lecture. Now we will continue from Snell's law of refraction. And in continuation to Snell's law of refraction, we need to cover the interference, diffraction, and polarization, spectrometry, and further more topics. So thank you all. Thanks a lot.